Everything we believed about Jupiter, its formation, its structure, the engine behind its magnetic field, has been dismantled by a single spacecraft the size of a basketball court. Juno didn't just observe Jupiter, it contradicted it. And the deeper it looked, the more unsettling the picture became. This is the story of what Juno found, and why it matters not just for Jupiter, but for every gas giant we've ever cataloged in the cosmos. Juno is NASA's most distant planetary orbiter, a solar-powered probe operating at the edge of what engineering can withstand. It spans 20 meters in diameter, not for elegance, but necessity. At Jupiter's distance from the Sun, a spacecraft receives only 4% of the sunlight available near Earth. Even with panels that large, Juno generates just above 400 watts, roughly enough to power a few household light bulbs. Launched on August 5, 2011 atop an Atlas V rocket, Juno didn't take a straight path to Jupiter. After escaping Earth's atmosphere, it looped into deep space, fired a small engine burn, and headed back toward Earth. 2 years after launch, it swung past our planet again, not as a detour, but as a slingshot. Earth's gravity accelerated Juno by over 14,000 kilometers per hour, sending it hurtling toward Jupiter with far less fuel expenditure than any direct burn could achieve. Elegant, efficient, and quietly brilliant, after a 5-year journey spanning 2.8 billion kilometers, Juno entered orbit around Jupiter on July 5, 2016. The risks were immediate. Jupiter possesses the most powerful radiation belt of any planet in the solar system, energetic enough to disable most electronics within days. The previous Jupiter mission, Galileo, suffered repeated hardware failures from radiation damage as it passed through the heart of that belt. Mission planners designed Juno to avoid the worst of it, threading a polar orbital path that grazed the planet at 4,200 kilometers above the cloud tops while bypassing the densest radiation zones to survive even that exposure. Juno was encased in a 1-centimeter shell of titanium, a tank, in essence, sent into the most hostile neighborhood in the solar system. Original expectations gave the probe roughly 20 months of operational life. Some instruments weren't expected to survive beyond the first 8 or 9 months. The mission was always understood to be a sprint. What happened instead is something no one fully anticipated. When Juno's camera transmitted the first images of Jupiter's polar regions back to Earth, scientists were genuinely unsettled, not in a minor way. Some researchers openly admitted they wouldn't have recognized the planet. What they expected was the familiar Jupiter, the one defined by its iconic horizontal bands, alternating amber and cream, stretching across the globe in neat latitudinal order. What they saw at the poles was something else entirely: massive, tightly packed cyclones, swirling in chaotic clusters, filling the poles with a density of storm systems unlike anything seen elsewhere in the solar system. The South Pole alone was ringed with 5 enormous vortexes. The North Pole had 8. These weren't temporary weather events. They held their positions with remarkable consistency across years of observation. Jupiter's atmosphere offered more surprises from within. Juno carried a specialized microwave radiometer, an instrument built specifically for this mission, capable of penetrating deep below the visible cloud tops. What it revealed was a dense column of ammonia rising from the cloud tops and plunging more than 350 kilometers into the atmosphere, concentrated directly around the equator. Scientists had expected ammonia to distribute itself more evenly throughout the planet. Instead, the gas appeared to be feeding upward through a narrow, concentrated channel in a pattern nobody had predicted. Jupiter, even at its most familiar, was hiding extraordinary complexity just below the surface. For decades, two competing models defined scientific thinking about Jupiter's interior. The first, gravitational collapse, proposed that Jupiter formed directly from the implosion of a gas cloud, no solid core, no central nucleus, just hydrogen and helium, all the way down. In this scenario, Jupiter would be essentially the same material from its outer atmosphere to its center, a fully mixed planet with no distinct internal boundary. The second, core accretion, argued that Jupiter began as a rocky and icy solid body, built from heavier elements like carbon, iron, oxygen, and magnesium. As this core grew massive enough, its gravity began pulling in hydrogen and helium from the surrounding solar nebula, eventually forming the gas giant we recognize today. This model predicted a well-defined, compact core with a clean boundary separating it from the surrounding layers of gas. Both were logical. Both had supporting evidence. And Juno overturned them both overnight. Juno was designed to map Jupiter's gravitational field with approximately 100 times the precision of any previous measurement. As it traced its elliptical orbits, plunging close to Jupiter, then arcing far out, tiny fluctuations in the planet's gravity caused minute changes in the spacecraft's speed. Juno was sensitive enough to detect velocity shifts as subtle as 0.1 millimeters per second. It transmitted a continuous radio signal back to Earth, and scientists used the Doppler effect to decode those tiny accelerations and decelerations into a detailed map of how mass was distributed inside the planet. What that map showed was neither a missing core nor a solid 1. Jupiter's core is diffuse, fuzzy. It doesn't end so much as it fades, gradually blending into the hydrogen-rich layers above it without any clean boundary. It spans roughly half the radius of Jupiter itself, far wider than any solid core model had anticipated. It is not a nucleus. It is more like a suggestion of one, a gradual concentration of heavier elements that dissolves into the surrounding gas envelope. The immediate explanation that scientists reached for was catastrophic collision. Perhaps Jupiter once had a compact, solid core, but early in the solar system's history, a protoplanet struck it with enough force to shatter and scatter that core into the surrounding layers. It was a tidy theory. Then someone modeled it on a supercomputer. Researchers ran simulation after simulation, varying the size of the impacting body, the angle of collision, the speed of impact. Every time, the same thing happened. The collision initially disrupted the core, but within millions of years, the dense rocky material sank back toward the center, settling out like sediment in a glass of water. The sharp boundary reformed. The model couldn't reproduce the fuzzy core Juno had measured. The explanation didn't hold. The next clue came not from Jupiter, but from Saturn. Data from the Cassini mission, combined with measurements of how Saturn's rings vibrate in response to internal planetary oscillations, revealed that large regions of Saturn's interior do not convect. In a fully convective planet, heat escaping from the interior would continuously stir the material inside, distributing heavier elements throughout. But if certain regions resist convection, heavier elements stay concentrated in the interior rather than mixing outward. The data pointed to a fuzzy core in Saturn as well, a compositional gradient rather than a discrete solid nucleus. To gas giants, same unexpected internal architecture. The collision hypothesis, even if it could be made to work for Jupiter, couldn't explain an identical outcome in Saturn. Scientists are now working toward a new model of gas giant formation, one in which fuzzy cores aren't a product of catastrophic events, but a natural outcome of how these planets form and evolve. The details remain unresolved, but the old picture, a compact solid core wrapped in a gas envelope, is no longer viable. This doesn't just rewrite Jupiter. It rewrites every gas giant we've ever studied, and every exoplanet we've ever classified as one. Jupiter's magnetic field has always been extraordinary by any measure. It is the largest and strongest of any planet in the solar system. Its magnetosphere extends 7 to 21 times Jupiter's own diameter, stretching so far behind the planet that its tail reaches all the way to Saturn's orbit, roughly 1 billion kilometers away. The field is generated through a dynamo process in Jupiter's layer of metallic hydrogen, a region beginning tens of thousands of kilometers below the cloud tops, where pressures and temperatures are so extreme that hydrogen transitions into a liquid, electrically conductive state. Jupiter's rapid rotation, a full day lasts only about 10 hours, stirs this metallic hydrogen and powers the dynamo. But Jupiter's magnetic field has always had peculiarities. It is significantly stronger in the northern hemisphere than the south. It has intense, localized magnetic concentrations, including a feature called the Great Blue Spot, a region of unusually concentrated magnetic flux. And it possesses two magnetic south poles rather than one. Scientists hoped that the discovery of Jupiter's fuzzy core might explain these anomalies. Instead, it deepened them. Juno data confirmed that, like Saturn, large regions of Jupiter's interior appear to be non-convective. For a dynamo to operate effectively, electrically conductive material needs to move. A stable, non-convective region disrupts that flow. Researchers modeled the effect of two potentially stable zones, one in the upper interior, one deeper down corresponding to the dilute core, and found contradictory results. The upper stable layer actually improved the model's ability to explain Jupiter's magnetic field. The lower stable zone, the fuzzy core region, did not. A fully stable dilute core produces a magnetic field nothing like the one Juno measured. Current theories propose that helium rain, droplets of helium condensing and falling through Jupiter's liquid hydrogen interior, the way oil sinks through water, may play a role. Others suggest Jupiter's dynamo operates in a fundamentally non-uniform way, driven by variations in density and electrical conductivity that no existing model fully accounts for. Juno's magnetic field. Data also delivered the first confirmed observation of secular variation in a planetary magnetic field outside Earth, meaning Jupiter's field is slowly changing over time. This variation was most pronounced around the Great Blue Spot and is thought to be driven by a dynamic layer at the base of Jupiter's atmosphere. Nobody knows exactly how this field works. The more Juno revealed, the more clearly the existing models fell short. One thing Juno clarified spectacularly is the scale and behavior of Jupiter's auroras. Unlike Earth's northern and southern lights, which appear only during certain seasons and at certain latitudes, Jupiter's auroras are permanent, covering both poles in continuous ultraviolet displays hundreds of times more energetic than anything seen on Earth. When Juno measured the direct electrical currents in Jupiter's magnetosphere, they weren't powerful enough to account for the aurora's brightness. The remaining energy is thought to come from alternating currents, generated by turbulence in the magnetic field. The difference between Jupiter's north and south auroras reflects this. The southern aurora is relatively structured and circular, consistent with smoother magnetic field lines, while the northern aurora is dispersed, filamentary, and chaotic, a direct reflection of the more complex magnetic geometry at that pole. Juno's infrared aurora mapper added another layer. In infrared, the aurora shows brilliant whites and greens, ions striking the ionosphere from space, and patches of red that scientists believe may be ions originating from Jupiter itself, a phenomenon never previously observed. Visible in the same infrared images are the distinct fingerprints of the Galilean moons, a bright spot and tail where Io's electromagnetic influence connects to the planet through a flux tube carrying up to 400,000 volts and 5 million amps of current. Fainter marks indicate where Europa and Ganymede leave their own electromagnetic signatures on Jupiter's ionosphere. When Juno completed its original 33 planned orbits in 2021, it was still in exceptional condition. The titanium shielding had done its job. Even the camera, expected to be one of the first components to fail, was still operational. NASA extended the mission for an additional 42 orbits and redirected Juno's attention to Jupiter's moons. Ganymede received Juno's first close flyby in June 2021, bringing the spacecraft to within 1,000 kilometers of the surface. The resulting images revealed its icy terrain in extraordinary detail: dark, heavily cratered ancient terrain alongside lighter, geologically younger regions, and the long structural striations thought to be fault lines produced by tectonic activity driven by Ganymede's iron-nickel core. Ganymede is known to harbor a vast subsurface ocean that some researchers consider potentially suitable for life. A concurrent Hubble observation produced one of the mission's more unexpected results. Scientists monitoring Ganymede's ultraviolet emissions in support of Juno's flyby expected to find oxygen, long suspected to be present based on prior spectral analysis. Instead, they found almost none. What dominated the thin Ganymede atmosphere was water vapor, a significant revision to existing models, and a finding that may have implications for icy bodies throughout the outer solar system. Europa received its close flyby in September 2022, at a distance of just 351 kilometers. High-resolution images showed a heavily fractured surface of ice ridges and grooves. More striking was a darkened patch identified by scientists as a likely subsurface eruption site, a sign of cryovolcanic activity forcing material upward through more than 10 kilometers of ice. A subsequent paper proposed that the dark feature might reflect not a deep eruption from the subsurface ocean, but from shallow brine reservoirs trapped within the ice shell itself, pocket lakes of high salinity liquid, expanding and occasionally bursting through the crust above them. Io became Juno's final obsession. Jupiter's third largest moon is the most volcanically active world in the solar system, its interior perpetually stressed by the gravitational tug-of-war between Jupiter's immense pull and the orbital resonance with Europa and Ganymede. Juno made multiple close passes at approximately 1,500 kilometers from Io's surface in 2023 and 2024, close enough to map its volcanic landscape in detail, image never before seen polar terrain, and observe active plumes rising above the horizon. The microwave radiometer revealed Io's surface to be comparatively smooth, an effect of constant renewal. As lava floods erase craters and fills depressions in a planet-scale process of geological overriding, Juno imaged the enormous lava lake Loki Patera to 200 kilometers across, its surface described as smooth as glass, and identified a second lava lake, Kurs Patera, through infrared mapping. It documented the Prometheus volcano, active in every observation since Voyager in 1979. It discovered 3 previously unmapped mountains in Io's northern polar region. Then, on December 27, 2024, came something unprecedented. As Juno executed a flyby, simultaneous eruptions ignited across a 65,000 square kilometer region of Io's surface. Hundreds of volcanoes firing at once, in apparent synchrony, an event interpreted as multiple vents connected to a shared lava channel network releasing pressure simultaneously. It stands as the most energetic volcanic event ever recorded in the solar system. Voyager's 1979 flybys had detected mysterious atmospheric flashes on Jupiter, assumed to be lightning generated by water ice clouds, requiring liquid water to exist at least 45 kilometers below the visible cloud tops. Juno's Stellar Reference Unit, a navigation camera designed for tracking stars in low-light conditions, detected those same flashes, but they were at the wrong altitude. The flashes were occurring far higher in the atmosphere than water-based lightning should be possible. At temperatures below -88 degrees Celsius, the explanation, the storms generating this lightning aren't water storms. They're ammonia-water storms. Ammonia acts as an antifreeze within Jupiter's atmosphere, combining with water to form a solution that remains liquid at temperatures far colder than pure water could tolerate. These hybrid thunderstorms generate electrical discharges and produce a form of precipitation that doesn't exist anywhere on Earth. Pellets of water ammonia slush falling through the upper atmosphere. Scientists have named them mushballs. Jupiter's weather is not a scaled-up version of Earth's weather. It operates on different chemistry, different physics, and different scales than anything interrestrial experienced. Juno was originally planned for shutdown in 2018. Its extended mission was scheduled to conclude by September 2025, with the probe deorbited into Jupiter's atmosphere, deliberately destroyed, to prevent any accidental contamination of the Galilean moons that might one day be investigated. For signs of life, the deadline passed. The US government experienced a funding shutdown. NASA remained quiet about Juno's status. Speculation circulated that the probe had been quietly powered down without public announcement. Then NASA published new analysis of Europa's ice shell thickness, referencing prior Juno data extensively, and closing with a single line. Juno would carry out its 81st flyby of Jupiter on February 25. Juno is still operating. Whether it will eventually be sent into Jupiter's atmosphere on a controlled trajectory, or whether it will continue transmitting science data, is not currently confirmed. What is confirmed is that this spacecraft, which was never expected to last beyond 20 months, which carried instruments projected to fail in the first 8, which was designed for 33 orbits and given 42 more, is still out there orbiting, measuring, transmitting. What Juno found at Jupiter is not a completed picture. It's an invitation to rebuild from scratch. The core isn't what the models predicted. The magnetic field isn't explained by any current dynamo theory. The moons carry subsurface oceans and volcanic systems more complex than anything anticipated. The atmosphere runs on chemistry with no terrestrial analog. Every answer Juno delivered came attached to new questions, questions the mission was never originally designed to ask. That is, arguably, the most honest result any scientific instrument can produce. Jupiter remains Jupiter. Strange, enormous, and only partially understood. And Juno is still looking.